All right. Now, before we get started with playing the game of Gauss-Jordan, um, you got to get fluent with converting a set of equations to an augmented matrix and vice versa. So in this first example, we're going to take sets of equations and just write their augmented matrix. We're going to write the augmented matrix corresponding to these systems of equations. All right. So just remember that all we're doing is taking the coefficients from the x and y terms, and that becomes the left-hand side of our matrix. So we have 2, 5, 3. Now this is a minus y, but it's the same thing as minus 1 times y. So the coefficient is a negative 1. Okay. And then the right-hand side is just these, the stuff that's on the right-hand side of the equal sign. So 1 and 10. And that's the augmented matrix corresponding to that system of equations. All right. So you can pause the video and go ahead and try this next one. I think it's pretty straightforward. You basically just take the coefficients and put them in a matrix. All right. So here's what we get. We have a negative 3 is the coefficient on the x. 7 is the coefficient on the y, and then we have 9 and negative 20. All right, so make sure you preserve the sign. So when it says minus, then it's the same thing as plus and negative 20, right? So it's really negative 20. And then on the right-hand side here, we have a negative 2 and a 4. All right, so that's the augmented matrix corresponding to that system of equations. Now we can do linear systems of equations with more than 2 variables. All right. Now, in effect, when we have more than 2 variables, if you think about graphing it, you'd instead of graphing in 2 dimensions, you would be graphing in 3 dimensions. So really, the system of equations represent planes instead of lines. But we'll get to that. But basically, it's the same idea. We're going to take the coefficients from the variables and put them in a matrix. So 2, 4, 6, 3, 8, 5. We have a minus x, which is the same as minus 1 times x. So that's a minus 1, 1, and 2. And then on the right-hand side, we're just going to write down these numbers, 22, 27, and 2. All right, so that's our augmented matrix. And finally, we've got one where we've just basically got x equals 4. We got the solution, basically, right? It's x equals 4, y equals 29, z equals negative 13. So we're going to write that as an augmented matrix. Now, in the augmented matrix, each column corresponds to a variable. So, and we usually put it in alphabetical order. So I'm going to call the first column the x column, right? So I'm going to have x, not x. I'm going to have the coefficient on x in this case is 1, right? So I'm going to have a 1 in the x column, and then I don't have a y value in that first equation. I'm just looking at this first equation. I don't have a y and I don't have a z value. And the number on the right-hand side of the equal sign is 4. Okay, so that's the way I'm going to represent that particular equation. X equals 4 becomes 1004. Okay, and then this should be a line here. Now in the second equation, I don't have an x value. I just have a y value, right? So that's 1 times y. So my coefficient on y is 1, and then I don't have a z value. So the coefficient on z is 0. And then I have a 29 on the other side of the equal sign. And the last equation, I don't have an x, I don't have a y, so it's the same as 0 times x plus 0 times y plus 1z, right? So it's just going to be a coefficient of 1. And then the number on the right-hand side of the equal sign is a negative 13. Okay, so that is the augmented matrix corresponding to that last system of equations. All right. All right, so that's all for that. Now, in the next example, we're just going to do the opposite. We're going to take augmented matrices and turn them into systems of equations.